Hello, and thank you for your interest in our presentation. DISPEC project is about improvements to the science data quality of ionospheric specification. I will be discussing one of the scientific data applications of DISPEC. Number 3, anomaly mapping of the ionospheric effective slab thickness. I am Ivan Galkin, and my co-authors are Adam Fron, Andrzej Krankovsky, and Manuel Hernandez Pajares. Together we represent two communities of remote sensing the near-Earth plasma. I am on the ionizond side, the Global Ionosphere Radio Observatory, GIRO, and my co-authors are from the community of Global Navigation Satellite System, GNSS. So this SDA, Science Data Application, is about the cooperation of GNSS and GIRO by means of computing real-time anomaly maps of the effective slab thickness, tau. There are three categories of global maps involved. Maps of the quiet time climatology that are computed using a climate peak electron density in F2 layer, NMF2. Obtained from IRI, International Reference Ionosphere Model, and Climate Vertical Total Electron Content, VTEC, a 28-day average VTEC, maps obtained from GNSS Ionospheric Product Coordination Center in Poland. Next, we will talk about real-time weather dynamics of tau, whose maps are computed using weather peak density from IRTEM, a real-time IRI project operated by Lowell GIRO Data Center, and weather VTEC provided by GIMS. Finally, the difference of two maps, weather minus climate anomaly map of tau, will be discussed. The idea that GNSS and GIRO can work together on ionospheric specification is not new. Previous success stories included the 2D global mapping of peak density and NMF2. By observing how different VTEC is from its quiet time reference, that delta VTEC, that difference would be attributed to the peak density, which supposedly helps for over no coverage zones of the world where no ionozones are available. Also, simultaneous assimilation of VTEC and ionozone measurements were attempted in the modeling designs based on the regularization of the differences. One clear issue with this approach was the greater number of VTEC values available from GNSS receivers than ionozones inputs, something that I called 6,000 versus 60 problem. Essentially, GIRO inputs were ignored in such direct assimilation of both instrumentation data. In GPC model developed by the NWRA team in California, that weighted assimilation was introduced to bring more weight to the GIRO data, ionozone data. But at this time, I'm not sure if that idea remained in operation of GPC. I do know that HF geolocation project in the US decided to avoid VTEC inputs to background ionosphere specification altogether for data quality consideration and applicability. Finally, the fusion idea is practiced, like in TID model, topside assisted by ionozone model, where the bottom side ionosphere is observed by digizond and the topside ionosphere model is placed at the peak and then manipulated into agreement of the ionospheric tag, which was obtained by a collocated VTEC system. Okay. Our idea for DISPEC is in the data fusion category. We suggest combining peak density and vertical total content to reason about so-called effective slab thickness. This is a rather artificial concept where the idea is to determine the thickness of a plasma slab whose length is equal to the peak density, and total area in gray is VTEC. This is computed by simply dividing VTEC by NMF2. Easy computation, not a complicated data fusion at all. Until the real-world problems are considered, neither VTEC nor NMF2 are free from the noise of their measurements. So DISPEC is responsible for careful analysis of data quality for computations of the tau value. But before we dwell into the topic of the data quality, let me say a few words about the utility of tau to the ionosphere weather monitoring. In the chart of the left, 3 density profiles are shown that have the same total amount of plasma, so the same VTEC, but different peak density. From the shape of these curves, it is now more intuitive that a thicker slab means elongated, stretched profile. A thinner slab is more compressed in the vertical dimension. Now, if you ever worked on modeling of HF signal propagation, that is important consideration. The slab thickness is certainly effective in impacting the ray tracing. Well, let me be careful here about my language. I said stretched and compressed, describing the tau thickness. But this is not quite what happens in the ionosphere. Plasma transport is usually not involved. It's more about chemistry modifications, mostly about ionization and recombination rates rather than physical squeezing or stretching plasma particles. But anyway, tau appears to be a proxy that indicates other processes in the ionosphere and thermosphere. We found out that it is sensitive metric to detect and characterize subtle changes in plasma. In fact, Professor Dietrich was an active proponent of tau science, suggesting its strong relationship with temperature and composition of the thermosphere and the ionosphere. A nice indicator of the vertical plasma restructuring, redistribution in the ionosphere, plasmasphere also, by a simple one-parameter characterization of the complete profile shape. Other connections are noted as well: vertical scale height, MUF, maximum usable frequency for HF communications, and etc. Now on to the data quality considerations. Here's a sample of the quiet time tau computed using IRI for NMF2 and IGS, the GNSS service, 28-day average VTEC. When Adam and I first plotted this man, we had a moment of panic. Tau exceeding 1,000 kilometers seems out of this world, not on Earth. We were expecting a few hundreds maybe, so we almost got discouraged. We thought that a small VTEC at the end of the night, do you see that terminator line for the dawn? Yes, there. So at the end of the night, VTEC is small, and then F2 is small, and two small numbers divided may become nonsense, affected by like low precision of the instrumentation. Until we thought of an argument that the sun ionization comes to the higher altitude first, and then it reaches the ionospheric height. So right before the dawn, sun begins making plasma in the plasmasphere, and so we get a high thickness of the slab. Our next moment of panic and discouragement occurred when we plotted our first anomaly map of the tau during a geomagnetic storm in November 2021. This is weather minus climate anomaly map in percent deviation from the quiet time behavior. Red color shades mean thicker slab than expected, and blue shades mean thinner slab than expected. So, and this is minus 75 to plus 75% deviation happening at the same time, simultaneously in different parts of the world, plus and minus. Well, granted, this is a storm time ionosphere, but how is this Persian rug pattern possible? What are these anomalies? Are they even real? So to test the sanity of our computations, I plotted the anomaly map of MOV 3000 next to the anomaly map of tau. So MOV 3000 is the maximum frequency of the signal that can propagate over the ionosphere to the receiver 3000 kilometers away. No VTEC is used to compute MOV 3000, only ionizon data. Remarkably, as you see, areas where MOV is depressed, look at these blue spots on the right anomaly map. These blue depressed MOV areas are important consideration for HF communicators. Low MOV means that your usual operating frequency is too high, it's not working. On the left, these spots correspond to a red color. So look, MOV anomaly of minus 50 to plus 50% is seen in the tau anomaly map as minus 75 to plus 75 anomaly. So higher than expected tau, so thicker slab, appears to be a very sensitive way to identify areas of low MOV. And here are the anomalously high MOV values. These are not that critical to your HF communications. So they, as you see, they do correspond to the anomalously low slab thickness. So compressed plasma, as you remember. So, well, there are two question marks on the left map. Low tau does not correspond to high MOV. These are areas where no ionizons are available. These are gyro no coverage regions. So we may have found a tool to sense MOV dynamics over the no coverage areas. We would also be able to make recommendations for setting up new ionizon observatories over these areas. Let me finish with this summary of the DISPEC work to do. We need to clarify the interpretation of the tau anomaly maps, because GNSS and gyro networks are different in their coverage. And the corresponding maps of VTEC and MF2 uncertainty areas differ as well. So graying out these anomaly maps over no ionizon or no GNSS receiver areas would be useful. One clear possibility is using the confidence metric from IR10. That assimilative model has certain proven spatial prediction capability, but the confidence score over such interpolated and extrapolated data outside the ionizon observatories is gradually reduced with distance away from the sensor site. We have that data confidence flag routinely calculated for the MOV 3000 maps we report to Pegasus. This is a civil aviation project. So that confidence flag can be used. We could also support the confidence evaluation with the comparison study of covariance ellipses in IRTM. These are not standard covariances. These are applied individually for different diurnal harmonics. We'll specifically study high-value tau cases for potential precision issues. And remember, those are the cases when a small VTEC is divided by small NMF2 value. And given that both data sets are subject to uncertainty because of the data noise. And we've also looked at the alternative ways of compute GIMS, both in terms of climatology and the weather and anomaly maps. On the climatology, is that 28-day average the best optimal for computing the quiet time reference for VTEC? And similarly, is IRI the best way of computing that quiet time reference, or we'd rather use a 28-day average of an MF2 measurements? As for the weather and anomaly maps do not use the averaging techniques or the instance of measurements, so their uncertainty concerns are also very important. Okay, this is it. Thank you for watching this to the very last slide.